Can you solve this math challenge? Here's the question. Solve for the integer values of x, y, and z, given that x squared minus y squared equals 24 and y squared minus z squared equals 16. You can pause this video if you want to give this problem a try. And now, let's answer this question together. So our goal is to find integer solution for x, y, and z, given this equation x squared minus y squared equals 24 and y squared minus z squared equals 16. Now, how do we answer this question? One thing to notice here is we have negative y squared and positive y squared on the second equation. So, if we add these two equations, we cancel out y squared. So, let's do that. Therefore, if we add this, we get x squared minus z squared equals to 24 plus 16 will give us 40. Now, let's focus on this resulting equation, x squared minus z squared equals to 40. Now, since we want integer values for x and y and z, take note that when we have a squared minus b squared, this can be factored as follows, a plus b multiplied by a minus b. So, the left-hand side of our equation can be factored as follows. We have x plus z multiplied by x minus z equals to 40. And then since x, y, and z are all integers, so we want integer factor of 40. Now, 40 can be factored as 1 times 40, can be factored as 2 times 20, can be factored as 4 times 10, or this can be factored as 5 times 8. So, technically, we have 4 major cases here. So, we have 1 times 40, 2 times 20, 4 times 10, and 5 times 8. Now, let's have the case number 1 first. So, x plus z multiplied by x minus z equals to 1 times 40. It follows that x plus z equals 1 and x minus z equals to 40, like this. Now, again, we need to solve for the values, integer values of x, y, and z. And take note, when we add these two equations, we cancel out z, so this will give us 2x equals to 41. Now, if we divide by 2 on both sides, 41 over 2 is not an integer. This is just 20.5. Therefore, this case number 1 is not possible. Also, when we add the factors and we get an odd number, that case is not possible. Now, example is case number 4. 5 plus 8 will give us 13, and 13 cannot be divisible by 2. Therefore, this case number 4 is also not possible, or we don't get any integer result in case number 4. So we can now eliminate case 1 and case number 4. This will leave us with the two major cases, case number 3 and case number 2. Now, let's start with case number 3. Take note, on this equation, we have x plus z equals to 4 and x minus z equals to 10. Now, if we add these two equations together, we get 2x equals to 14. Divide by 2 on both sides, we get that x equals to 14 over 2, or simply equal to 7. Now, if x equals to 7 and x plus z equals to 4, therefore, we can say that z must be equal to negative 3. Now, take note, this is possible because 7 squared minus y squared equals 24. 7 squared is 49, and 49 minus 24 is 25. And 25 is a perfect square, so we get the value for y. Also, if z is negative 3, so negative 3 squared is positive 9. 16 plus 9 will give us again 25, so we get again an integer value for y. So this case is good. Now, let's continue. Case 3.1, we have x plus z multiplied by x minus z must be equal to 10 times 4. It follows that in this situation, x plus z equals to 10 and x minus z equals to 4. Doing the same thing on case number 3, we get the value of x equals to 7 and z equals to 3. Now let's focus on the next case, which is case 3.2, wherein x plus z multiplied by x minus z must be equal to negative 4 times negative 10. In this case, we get the value of x as negative 7 and z must be equal to 3. For the last case, case 3.3, we get that the value of x must be equal to negative 7 and z equals to negative 3, wherein x plus z equals to negative 10 and x minus z equals to negative 4. So, on case number 3, we get that x equals to 7 and z equals to negative 3. 3.1, 3.2, 3.3, we have those values for x and z. So now, let's move on to case number 2. On case number 2, x plus z multiplied by x minus z equals to 2 times 20. It follows that x plus z equals to 2 and x minus z equals to 20. Doing the same thing, add these two equations, and we get the value of 2x equals to 22. Divide both sides by 2, we get that the value of x must be equal to 11. Now, if x equals to 11 and x plus z equals to 2, it follows that z must be equal to negative 9. But take note, if we use this equation, y squared minus z squared equals to 16, and if we let z equals to negative 9, so we have y squared minus negative 9 squared equals to 16. Negative 9 squared is definitely equal to 81. And now, if we add 81 on both sides, we get that the value of y squared must be equal to 16 plus 81. And 16 plus 81 is equal to 97. And 97 is not a perfect square. So, on this case, we don't get an integer value for y. Of course, y and z here is not also an integer. Therefore, case number 2 is not possible. So the only possible case left must be equal to this case, case 3, case 3.1, case 3.2, and case 3.3. Now, we are now ready to solve for the value of y. So, using the second equation, because this is much simple than the first, so we have y squared minus z squared equals to 16. Let's substitute the value of z. But at this point, whenever we substitute positive or negative 3, we get the same result. So, we have y squared minus positive or negative 3 quantity squared equals to 16. Because positive 3 squared is still 9, and negative 3 squared, again, is 9. So, this is just 9. Add 9 on both sides, and 16 plus 9 will give us 25. Now, square root on both sides to get the value of y. And take note that we have two possible values here because x, y, z are all integers. So it can be negative or positive. So we have, on the left side, we have y, and on the right-hand side, we have positive or negative 5. Therefore, case 3 must be equal to when x equals to 7, z equals 3, and y must be positive 5 or negative 5. So we have these two cases here. So we have x equals to 7, y equals to 5, z equals to negative 3, x equals to 7, y equals to negative 5, and z equals to negative 3. On case 3.1, we get the same thing also, y equals to positive 5 and negative 5. So this will give us another two results for x, y, and z. On case 3.2, again, another two results. Because if y equals to 5 and y equals to negative 5, so if x equals to negative 7, y is 5, z equals to 3. X equals to negative 7, y equals to negative 5, then z equals to 3. And for the last time, the last two pairs of x, y, z must be given by this case 3.3, wherein x equals to negative 7, y equals to 5, z equals to negative 3, x equals to negative 7, y equals to negative 5, and z equals to negative 3. Therefore, we found this result using this equation x squared minus y squared equals to 24 and y squared minus z squared equals to 16, wherein x, y, z are integers, and here's our answer. So we have 8 possible triples. And as always, we are done.